Hello, grade 10s. We're going to be continuing on today with our study of light and geometric optics. So today we're going to be looking at lesson 2, which is reflections and plane mirrors. We are in your textbook in section 10.3 and 11.1. The pages that have to do with today's lesson are 402 to 405 and 416 to 419. So what we're going to do today, just a quick refresher on what we talked about yesterday in terms of the wave model of light, and then we're going to extend that to a new model called the ray model of light. We're going to talk about how light can interact with different types of materials, and compare and contrast transparent, translucent, and opaque materials, and then talk a little bit about reflection. So we're going to talk about the laws of reflection, different types of reflection, and how we draw it. So learning goals for today, by the time at the end of this little video lesson, we should be able to describe the properties and behavior of lights in terms of the ray model of light, in addition to the wave model of light we talked about yesterday. We should be able to compare and contrast transparent, translucent, and opaque materials, as well as be able to describe how light behaves when it's reflected and predict its angle of reflection. Okay. So yesterday, this is a copied slide from yesterday's lesson. We said, yesterday we said that the model of light we were going to talk about was the wave model of light. So we talked about how light can be modeled in a wave, and some properties of light can be very well explained using the wave model of light. For example, we talked about how color and color perception can be better explained if we look at light as though it's a wave. But we did say it doesn't explain everything. So today we're going to be looking at another model of light and looking at the types of things that can be better explained using what's called the ray model of light. So in the ray model of light, instead of describing or imagining light as these waves that are moving through space, we imagine them as moving as straight lines. So rays are always drawn. Rays of light, which is like a straight line that's used to represent light, are drawn to show the direction of light from its source. So for example, if we have a lamp here, we can see straight lines going out, and you can see the arrowheads indicating the direction of travel. This is saying like the light bulb here is producing the light, and all the light is moving out in these rays moving this way. Okay. So again, each ray ends in an arrow like we can see in this diagram to show the direction that it's continuing on in. It can also tell us about brightness. In general, the more rays that you see coming out of a source, the brighter that light is being produced by that source. So for example, this lamp has 1, 2, 3, 4, 5, 6, 7, 8, 9 rays. If it was beside another drawing that only had 6 rays, we would know the light bulb that was giving off 9 rays is supposed to represent a brighter light bulb. Okay, if it was standing beside a different picture of a lamp that was giving off 12 or 13 rays, we would know that the other lamp, the 12 or 13 ray lamp, would be the brighter one. Okay, so it tells us about direction of travel of light and also relative brightness. The neat thing about light, especially when we're talking about the ray model of light, is that light will travel in a direction until it hits an object. And different materials are going to interact in different ways. Okay. Some materials are going to allow light to move right through it. Other materials are going to allow some light to move through it, and other objects will allow none. Okay, so sometimes there will be reflection or absorption of light depending on the types of materials that you come through. Okay, that's also going to dictate how much we can see through that object. So when we think of like a plastic cup versus sort of some semi-clear cup and an entirely clear cup, the reason why we can see different amounts through these 3 cups is depending on how much light it allows to move through it versus absorbing it. Okay, so the 3 types of materials we're going to talk about are transparent, translucent, and opaque. Transparent would be like clear glass or clear plastic. Okay, these types of materials absorb very little light, which means light very easily passes through it. Okay, so if I have something like a clear sheet here or glass at my window, okay, I can see through that very easy. So we would call those transparent materials. Okay, so clear glass and clear plastic are great examples of that. Okay, so again, it's absorbing very little light and allowing a lot of light to move through it, which is why we can see objects on the other side of it. Okay, because the light's bouncing off those objects that we're seeing past it instead of the object itself. Okay, so anything that you can see through very easily, like a clear window or a clear piece of plastic, would be considered transparent. Translucent would be more like frosted glass, okay, or like sheer materials. Okay, like if you have like a very sheer window covering, so you can still kind of see through the window, but not completely through because of, say, a thin pair of drapes. Okay, my cup here, or even my lemon juice water, okay, this is a good example of something that's translucent. I can kind of see, like you can kind of see the straw in the water down here. It's a little cloudy. It's not as clear as a perfect glass window, but because I can kind of see my hand through it, okay, it's more of like a frosted effect. Or even because this plastic is a little bit thicker and the image that I'm seeing through it, if you look at my face now, it's a little bit distorted. That would be more of a translucent material, okay? So some light is able to move through it, but some of it is still absorbed. Okay. Opaque materials would be something like my calculator. If I put my calculator in front of my face, you can't see my face anymore because all of the light's being absorbed or reflected off this object. None of the light can actually pass through. So you can't see what's behind it in the same way you can see what's behind a transparent or translucent material to some degree. Okay. So transparent things we can see through very easily. Translucent things you can kind of see through, more like frosted or somewhat of a fuzzy image. Opaque things you can't see through. Okay, which means transparent allows almost all of the light to move through it. Translucent lets some of the light through it, and opaque lets no light through it. It absorbs or reflects all of the light. Okay, so here's a picture diagramming the same thing. We can see this is a ray model of light being represented instead of the wave model. We can see these rays coming off and we see the direction they're moving. Transparent, like clear glass or plastic, all of the light is going right through that object. So it's a clear, crisp image on the other side, okay, and you can't actually see this material itself very well. Okay, translucent would be like somewhat clear, frosted glass. You can see a lot of the light is moving through it, but some of it is being absorbed or reflected back. So you can see this material a lot easier, but you still can see the other side relatively easy. The last painting that we have here on the back is opaque. You can see all of the light is either being reflected or bounced off that object. You can see the object itself very easy. You can see this like white sheet of plastic very easy, and you can't see anything of what's on the other side. Okay. This diagram is also from your textbooks, figure 10.45, if you want to take another look at it. Okay. What about, though, objects like a mirror? In a mirror, you can't see what's on the other side of it, but you're seeing an image in it. How do those work? That's a little bit different than the transparent, translucent, or opaque materials we've already discussed. Well, that is all caused by something called the law of reflection. So what we see in geometric optics is smooth, shiny surfaces like calm water, where we can see here, or glass or metal at times can allow you to see a reflected image via the law of reflection. So like, for example, a mirror would be a great example of something that you're seeing through the law of reflection. The smoother the surface, the more clear the image is going to be. And essentially what happens is an image would be a reproduction of an object produced by an optical device like a mirror. Okay? So for example, here is an object, a horse. What we're seeing here, the reflection here in the lake, we would call its image. It's a reproduction of this object by an optical image or something like a mirror. And in this case, the optical device is the water itself. Okay. Or if I go into my other room to get ready and I'm doing my hair or putting on some makeup, when I can see my image in the mirror, I am the object, and my reflection in the mirror would be the image. Okay. So how this is caused is light rays bouncing off an optical device like a mirror in a similar way, if you've ever played hockey, to a puck bouncing off the boards. Okay. So if I shoot the puck and it hits the boards, we know it's going to bounce off the boards and come back. Okay. The same thing happens to light and things like mirrors. Okay. Remember, we can only see things when light bounces off them and goes into our eye. So what a mirror does, for example, is light bounces off the mirror back into your eye to show you the image of your face or whatever you can see in the reflection. Okay? And that process is called reflection. So again, I can only see objects because light reflects off them. So if this is a mirror, I can see maybe here's my face. The light that's coming off my face is going to bounce off the mirror and then bounce back off of it in a regular fashion. The more organized this reflection, the clearer the image is going to be. And as long as this can bounce back into my eye, I'll be able to perceive that image. Okay. So what's happening here? You can see the girl's face right here. There's going to be a light that, say, came in from the light source, whether it be the light in the ceiling or light from a window, comes off, bounces off her face, goes towards the mirror, bounces off the mirror, and then comes back into her eye so she can perceive the image of herself. Okay? If there is regular reflection, now regular reflection is if rays of light going in are parallel, they bounce back out parallel, you will be able to see a clear image, okay? And you'll be able to very easily see a reflection. And this happens in very smooth devices like a mirror, okay? But we know we can't see a reflection in all things. If I hold my calculator up and I look at it, I can't see a picture of my face in the back of it. And that's because this calculator doesn't have regular reflection, okay? When objects aren't shiny enough or when they don't have a smooth enough surface, you're not going to see regular reflection, which means parallel rays going in are going to bounce off in a bunch of different directions, okay? This may be because the surface of the object is rough, okay? And then when the light scatters in random different directions, that information can't reflect all back into your eyes, so you're not going to be able to see an image. So that's why when I look into things that aren't like mirrors, I'm not going to be able to see my reflection in it because it follows what's called diffuse reflection instead of following regular reflection. Okay, and it has to do with what happens to the rays of light when they bounce off that object. Okay? So, how do we draw these reflected rays? Now, if this is the mirror where reflection is going to come off, 90 degrees to that mirror, you're going to draw something that's called the normal. Okay, so this is exactly 90 degrees, right angle, okay, from the mirror. Now, if you look at the ray of light going in, okay, and you measure the angle using a protractor from that ray to the normal, that's called your angle of incidence. Okay, I used to remember that's the angle going into the mirror. It's going into the mirror, so it's the angle of incidence. We'll start with N. So the angle going in is going to be your angle of incidence. When it hits the mirror, it's going to bounce off and reflect. Okay, and we can measure the angle again from this ray, the reflected ray here, what's coming off the mirror back to the normal. This angle right here, if you measure it with the calculator, is going to be called the angle of reflection. Now, in regular reflection, okay, the angle of incidence is always going to be equal to the angle of reflection. So if this is 30 degrees, this is going to be 30 degrees. If this is 40, this is going to be 40. If this is 90, this is going to be 90, okay? These two angles are always going to equal one another. So how we would write that out or explain that is it says when light reflects off a surface, the angle of incidence, what's going into the mirror, so the angle from that ray going in to the normal is going to equal the angle of reflection, okay? Or the angle from the reflected ray back to the normal as well. Okay, often we represent these angles with the Greek letter that looks like this, an O with a line through the center. It's called theta. So you can write this mathematically saying theta I, or the angle of incidence, the one going into the mirror, is going to be equal to the angle of reflection, or theta R. Okay, so this is essentially just saying in short form that the angle of incidence is always going to equal the angle of reflection. Okay. So this is why we can very easily see a regular image reflected in something called a plane mirror. So a plane mirror is like what you probably have in your bathroom. It's any mirror that's a flat surface instead of a curve. So if you have a big mirror above your sink, or if you have a mirror in like a compact, okay, if it's flat, we call that a planar mirror, okay? And when you look into a planar mirror, you're going to see your image as though you are on the opposite side of this magic portal on the exact same distance from the mirror. Okay? So if I need to look closer at something, like there's something in my eye and I need to look closer in the mirror, if I physically get closer to my mirror, my reflected image is also going to look like it's leaning into the mirror from the other side and perfectly reflect me. Okay? So oftentimes these types of mirrors, we describe them as like looking through a portal or through a window of a mirrored universe or a reflected universe on the other side of that mirror, even though there's nothing there. These types of images that are produced when it looks like someone is standing somewhere they're not is called a virtual image. Okay? So a virtual image is when there's no real image where we perceive it to be. So for example, if this dog is looking into the mirror right now, it looks like on the back side of this mirror, standing behind there, there's another dog. But if we go behind the mirror, you're not going to be able to see like a ghost dog behind the mirror because of the reflection. Okay? We're perceiving an object to be where it's not. So if my calculator is the mirror, and I'm looking into the mirror like this, it's gonna perceive to me, or my eyes are gonna think that there's another version of myself right here. But if I was to actually look on the other side or have someone look on the other side of the mirror, there's obviously not a floating Miss Zuliani right here. Okay? So I'm perceiving an object to be somewhere that it's not. So we call that a virtual image. Okay? So a virtual image is any image formed by rays that don't actually pass through the location of the image. So if this is my mirror, it looks to me like there's a Miss Zuliani standing right here, but because there's actually no light getting here, all of the light's just bouncing back towards my eye, none of the light actually gets in behind the mirror, this is a virtual image. So because where it looks to me like the dog is or my face is, there's no light there, that's called a virtual image. This is a little bit different. We're going to talk in the future about real images, where we use things, for example, like mirrors and projectors to actually project an image onto a screen where there is actually light where we perceive the image to be. Okay? The other neat thing about planar mirrors is if you look in a planar mirror, your left hand is going to appear to be your right hand on the other side. So everything is sort of flipped. Okay? So you can see this arm right here that she's putting on her lipstick with, if you think about it, is her right hand. But in this image that's being reflected, it looks like it's her right hand. Okay? If it was her left hand, her hand would be coming from this side of her body up towards her face. Okay? This is the same way if you're wearing a shirt with text. Like tonight, if you want to see this, put on some sort of shirt that you have that has a logo or writing on it and look in the mirror. The text is going to be flipped. It's going to actually be backwards in the mirror. Okay? So because the light is just reflecting and bouncing back, things that are on the left in real life are going to be perceived to be on the right, and things that are on the right in real life are going to be perceived to be on the left. Okay, so to review today's work. Now this is going to be really important. This week we're going to be finishing off the week looking at planar mirrors, and tomorrow you're going to be looking at how mirrors and different optical devices and waves and visible light are used in technologies. Next week we're going to start looking at how reflection works in curved mirrors, which are a little more complicated. Okay, so it's going to be important that you have this stuff down before we move on to the new stuff. So we're in 10.3, okay, and 11.1 of your textbook, okay. And I'm just going to write these down so I can pull these up in case you forget how to pull these up on your textbook. Okay, so remember, if you're looking for your textbook, we go to pearsoncanada.ca/Pearson eText. If this isn't bookmarked already in your browser, okay, make sure that you've bookmarked that. So go to this website. Okay, you're going to log in. Now, all of you have a number. You should already know this. It should be Tommy 10 text and some sort of number. Okay. If you don't remember your number, it is posted on the activity from today. Okay. You also just may want to save the password. Okay. The password as well is a capital T O M M Y 1010 TEXT. Okay. So Tommy 10 text. This is your password. Okay, just ignore the numbers, but there does need to be a capital T O M M Y 10 TAXT. That's your password. You're going to sign in. Okay. Click here. You may see a prompt that says, for example, yep, here we go. Pearson eText requires blah, blah, blah. Just press Get Flash and press Allow. Okay, textbook works. All right, so we have questions on page 406 and 420. You do this a few ways. You can just go right in here to page 406. It's going to take you right there. You also can say, well, we're in Unit D right now. We're in Chapter 10, 10.3, and then scroll your way through. I like to look at it like this, and I like to look at it this so you fit the page, and then you can scroll your way through to 406 if you want. Okay, so the first set of questions that you need to do right here is the learning checkpoint, question 1 through 4. We're also going to be looking at page 420 in section 11.1 of your textbook. Right here, question 1 through 4. Okay, so that's our homework for today. You can complete that in a Google Doc, okay, and submit your answers to your questions on Classroom under your assignment tab. Okay, hopefully that's clear for today. I hope everyone is staying safe, staying healthy, and staying at home. Hopefully we will be working together soon, and have a great rest of the day.